Hello, welcome to tonight's podcast on kinetics, which is understanding the rate of disappearance of reactants and how fast products are appearing. This is a very quick review so that you don't understand what kind of problem you're looking at for your test or your quiz. Rate deals with change of something, final minus initial, okay? And so this rate of change is change in concentration, final minus initial, over change in time, final minus initial. How fast I'm talking right now, between 0 and 10 seconds. If I'm talking really fast like this, you can measure how many words are coming out of my mouth per minute over change in time versus the rate of my voice right now, which is slow. And you can measure between whatever time I started talking slow to when I stop. That tells you rate of something, okay? So if you look at this right here, and I know it's blurry, sorry, the decomposition of N2O5, okay, and forget this NCCO4, but this N2O5 is disappearing. How do I know that? At time 0, I have 1.46. I'll write it in for you so you can't see it. At 7:53, I have 0.89. And at 1986, I have 0.43. What's going on, molarity-wise? It's decreasing. That tells you that when you start at 0, that this is a reactant. It is reacting, and the key word here is it's disappearing. So if it's disappearing, I want you to find the rate of disappearance between 786 seconds and 1986 seconds. What's happening between these two times? Not between any other times, but between those two times. Well, how would you do it? Well, you'd follow this equation, okay? And you would take the change in concentration, which is final minus initial, remember? 0.43 molar minus 0.89 molar over 1986 minus 753, and that's seconds. Okay. Now, when I do my math, I actually come up with 3.73, and it's negative, times 10 to the 4th molarity per second. Now, what's that mean? That means that this N2O5 is disappearing between these two time periods at a rate of 3.73 times 10 to the minus 4 molarity per second. Why is this negative here? This negative here is because it's decreasing. It's going away. It's disappearing. So if you don't like that negative, it confuses you, get rid of it and simply say that it's disappearing. Put that word in there, and that's how fast it's going away. You also have to be able to look at this graphically. If I still look at this graph right here, I've got two things going on. I've got two reactants, and these two reactants are hydrogen and ICl. Over here, you can see them labeled. If you notice, this starts higher and this starts lower, and I know the reactants because at time 0 I have stuff, right? I have something. Versus the blue line, if you look at time 0 right here, I have none. But at time 0 I have something, and if you notice there's a 1 to 2 relationship here, and so that's why this is disappearing twice as fast as this, because of that 1 to 2 relationship. And if you look at these points on the graph, those relate to points not on this chart or diagram, because this chart and diagram is not the same thing, but that's how you would find it out. You would tick-tock, have a watch, and that this time you'd measure, this time you'd measure, and you'd graph it. All right, now, what about this situation here? I've got blue lines on here. I know that these are my products because they are appearing. This has got to be my HCl because it's appearing twice as fast as this because it's a 2-to-1 ratio. Okay, and it's at time 0, I've got nothing, so they're products, right? There's none of this here. You put hydrogen and iodine chloride in, and there's none of this here to start with. As it's produced, it increases over time. Now, if you notice, these lines even out, and that's equilibrium, but that's a different chapter. Now, let's say I found the rate of disappearance for hydrogen. I did a problem using rate equation, the rate equation. And I found that hydrogen is disappearing at a rate of 3 molarity per second. So I've got 3 molarity per second that hydrogen is going away. And I want to find out how fast this is going away. So to do that, I'm going to use my stoichiometric relationship, my coefficients, and 1 mole of hydrogen is disappearing, while 1 mole of ICl is disappearing. And we already said that it's disappearing twice as fast, and so indeed it is. It's disappearing at a rate of 6 molarity per second. Now, if this was negative, why would it be negative? Oh, because it's disappearing. Then this would also be negative, wouldn't it? Because it's also disappearing. Now, let's go ahead and look at my rate of appearance of my two products. So here's my product, iodine. Okay, and I actually want to change my marker colors here so you can see the difference. Now, why is that negative there? Because it's disappearing. 1 mole of hydrogen goes away while 1 mole of I2 is produced. So it appears at the same rate that hydrogen is disappearing. Now, this is a positive number. And the reason it's a positive number is not because this is a negative number. This here means it's disappearing. This here means it's appearing. So again, if that bothers you, get rid of it, and you simply say that this is disappearing, right? This disappears, and this appears. And you just simply get rid of that negative and positive. So let's look at the HCl. Now, if you're looking at this at all and thinking about it, you know that hydrogen is going at a rate of 1, and HCl is being formed at a rate of twice as much as this is going away. So you know indeed that it's going to be twice as much. It's going to be 6 molarity per second. That's how much it appears. Right? And if I was doing that mathematically, I'd show that as a positive. So that's when you use stoichiometry and you look at the coefficients in an equation. That's one of the very few times you do this with rate and rate law. But this is rate, right? Now, what's true about rate and rate law? Well, rate is this. Change in concentration over change in time. Rate law is this one right here. Rate equals K, a rate constant. I spell it with this little k, not capital K because that's equilibrium, of concentration of A, whatever A is, to the n power. We'll talk about what that means in a second. And the confusing thing is, this is rate, and this is rate law, but what's it say here? It says rate, but it's not rate, it's rate law. They want you to fill in the blanks and say it's rate law. And to confuse things even more, these two equations are equal to each other. This equation here is equal to this equation here, through magical math. So what's rate again? Change in concentration over change in time. What kind of information do you see? You see a diagram that has time and concentration, a table. You see a graph that has reactants going away and products being produced. Now, we just looked at this rate law. There's two kinds of rate laws. We're going to deal with integrated rate law later. Right now we're going to talk about the differential rate law. That's exactly what we just looked at. And the reason why it's called differential rate law is because calculus is performed. You don't do it. Someone else did it. And the reason why this is integrated rate law, which we'll go into later, is because calculus was performed behind the scenes. And when that calculus was performed, they figured out that rate equals rate law. Oops. There we go. Okay, so rate equals rate law. They're both equal to each other. This is rate, and this is rate law. But they both say the word rate in front of them. Got that? Okay, so let's look at this information here. This is rate law. And so when I have rate law, I'm looking for this kind of information. Rate equals, okay, right, that rate constant, times my ingredients to a power. And my two ingredients here, my two reactants, are HgCl2 and this ion here. I can put those in brackets, and that's my rate law that I just wrote. That's the form I want to write it in. So let's look in words to see what we can figure out, and we'll do some math as well. So what happens, and how do you know you're finding a rate law? Well, you have a table that shows this experiment 1, experiment 2, experiment 3. And in experiment 1, what happens? This HgCl2 is kept the same. Those concentrations are kept constant. You don't change them because you want to see what happens when you actually find this out right here. So when I find this out, I need to get my calculator to make sure I'm doing this right. Let me just check something real quick. Okay, so when I double my concentration, this doubles, right? So I'm from 0.15 to 0.30 in experiment 1 and 2. This goes up by 4. So if this is doubling, I double it, and this increases, the rate increases by 4, it makes it go faster, 4 times faster. Then what did I have to do to this? I just square it. So that means this ion between experiment 1 and 2, and for this whole experiment, is something called second order. Whatever I do to this, I'm going to raise it to the second power. So if this is 2 in this case, 2 to the second power is 4. What would it be if I tripled it? Well, 3 squared is what? 9. So whatever I do to my ingredient, I square it, and that gives me what happens to the rate. Okay? So we'll get comfortable with this in a second. Now, what's happening between experiment 2 and 3? Well, between 2 and 3, this is kept the same now, isn't it, at 0.30? What happens here? This is being doubled. 3 to 2, that 0.0052 is being increased by 2 to make 0.105. And this is being doubled. So when I keep this the same, and this doubles, the rate doubles. So that means I double this, and this doubled as well. So that means I raise this to the first power, which means this is first order. So let's talk about experiment 2 and 3 real quick. Okay, we'll go back through here again, and we'll talk about how you talk about it in a sentence. I would say in a sentence, to explain what I just showed you, that in experiment 2 and 3, when the concentration of this C2O4 2- ion is kept the same, and the concentration of this ion right here, this compound, HgCl2, is doubled, right? It doubles. I take 0.052 and double it to 0.105. The rate doubles. So when the concentration of this ion is kept the same and the concentration of this reactant is doubled, the rate doubles. Therefore, I can tell you that this is a first order reaction, because whatever I do to this, the same exact thing happened to the rate. Now, you'd have to say every single one of those words to get your word description correct. Let me show you how to do math. So to do math, and this would be your question, find the rate law. So I'm going to find rate. Actually, let me make this a little bit smaller over here and smush it. Rate equals the rate constant times HgCl2 to a power of n, and then C2O4 2- to a power of m. All right, I'll go ahead and write it here so you can see that. All right, I don't know if I like that right there. There you go. Okay, now, how do we do this? Well, we're going to go ahead and we're going to look at the experiments just like we just did with our words. So let's look at 3 and 2. I'm going to be smart. I'm going to put experiment 2 over experiment 3 because experiment 2 has larger values. I'm actually going to use this equation and write out the format of the rate for experiment 2. So if you look for the rate in experiment 2, this is the rate, 7.1 times 10 to the -5th molarity per minute in this case. That's equal to K times the power of, concentration of both of these to the power of n and m. So I look under HgCl2 for number 2 and it's 0.105. I look under C2O4 and it's 0.30. And these are molarity. Now I'm just going to show you these units for this first one. You need to write it for the other ones, but I'm just showing you why, because they cancel out. And I look at rate for experiment 3, 3.5. I'm just looking at my chart, right? I look at my chart right here. Times 10 to the -5th molarity per minute is equal to K, because that's my format here, right? K times the concentration of 0.052 to the N and 0.30 to the M, and these are both molarity as well. So what's going to happen? If you look, my K's cancel. My molarity per minute cancels. This cancels because it's the same, and I'm left with the numbers of 2 equals 2 to the n, because when you divide this into each other, you get 2 to the n power. Well, what is n, you say? N equals 1. So by doing this, I just found out that this is first order, which means what? When I double this, this doubles. When I double the concentration, the rate doubles. Okay? Right now, let's go ahead and not clear everything, but we're going to use the same format to find out the information between experiment 1 and 2. And why am I choosing experiment 1 and 2? I'm choosing experiment 1 and 2 because I'm keeping the concentration of this the same and changing this. So I'm going to be smart again, and I'm going to put experiment 2 on top over experiment 1. I look at my rate for experiment 2. And again, I'm not going to write the units because you know they cancel, right? Over 1.8 times 10 to the minus 5. And you can write it as you go along and fill out the whole chart, or you can do it like I am and just do it component by component. Now, I already know this is to the first power. So now I'm going to say, I don't know what this is. I'm going to go ahead and put it to the m. And what do I know about HGCL? It's 105, 0.105. This is 0.30, and this is 0.15. So what's going to happen? K is going to cancel. This cancels. 0.105 to the first power over that is the same thing. Okay, and what happens here? This happens to be 4, 3.9 something, so it's 4, over 2 to the m. So now what is m? M is equal to 2. And what does m equal to 2 mean? That means that this is second order. Okay, I'm going to change that up there. Sorry, that's kind of messy, guys. I know it didn't record right, so I'm doing it over again. So you can kind of take what you can get on a Friday night here. So if you think about this, what happens? That means when I double my concentration of this ion right here, the rate went up by 4. So that means this is second order, because if this doubles, then this goes up by 4. Right, so we have our rate law now. And what is our rate law? Our rate law, from the other page, equals K times HGCl2 to the second order. Is that right? Or the first? I think it's the first. Yep, it's the first. Sorry. To the first times, sorry, I ran out of space here, C2O4, 2 minus, to the second. So that's my rate law. Okay? And actually, let me rewrite that so it's clearer. And why don't I shrink this a little bit? Okay? And that way that gives me more room to write my rate law. And I'm still not going to have enough room. I just write too big at the beginning. Thanks for being patient. Right now, I want to find the overall order. That's easy. I look at my exponents. I have first order for HgCl2 and second order for that ion right there, the C2O4. I'm going to go ahead and add 1 and 2 equals 3. That's my overall order. That tells me how much changing my reactants affects my reaction. So what's this tell me? Well, if I had an overall order of 5,000, what would that tell me about my reactants if I had these same two reactants or similar reactants and I changed them? If I changed the concentration, it would make the rate go crazy. What's this do? This doubles it and this quadruples it. So overall order, the lower the overall order, it tells you how reactive or how influential changing the concentration of the ions are on what's going on in a reaction. So I don't want to clear annotations, I want to clear this because my next thing, so what are the two items that we've asked you to do here, or I've asked you to do? Find the rate law, which we did. That's what this is. Find the overall order. And now we're going to find the value of the rate constant. So what's the rate constant? Oh, that's K, isn't it? So if you look at K, I want to find what that is. Now, to do that, this is my equation for my reaction. For this information here and any other experiments I come up with at a certain temperature, and usually they give you a temperature, let's just say it's 25 degrees, because if I change a temperature, don't I influence how fast or slow a reaction can go, right? Usually if it's hotter, it goes faster. If it's colder, then it goes slower. So to find K, I'm going to go ahead and write my equation like this. Rate equals HgCl2 to the first power over C2O4 2 minus squared. And that is equal to K, isn't it? All right, I'm doing this because I want to look at your units later, but I'm just going to go ahead and plug numbers in. If I plug my numbers in, I'm actually going to take, doesn't matter which one you take, so let's just take experiment 3. Always do the same thing. So I always go back to the bottom one of my chart, and I'm going to say that 3.5 times 10 to the minus fifth molarity per minute divided by 0.052 molarity to the first over 0.30 molarity squared. Those are my units for what my reactants are plugged into the rate equation. When I do that, I get a value of 0.00747, or 7.5 times 10 to the minus 3. Now that's the number for k. That's equal to k, my rate constant. But what I need to worry about now is I need to worry about what my units are. Okay? So I'm going to go ahead and get rid of this right here. I'm going to write my units over here so you can see what happens as far as units canceling out. I'm going to go ahead and show you the shortcut. So what do I have here? I have molarity per minute on top. And I have molarity here because it's the first power, and molarity, right? Because I've got molarity squared here. So this is really molarity, and this is molarity, yes? So now what happens? My molarity here cancels out, leaving me a 1 on top and 1 less molarity down below. So now I have 1 over minute over molarity squared. And what is molarity? Molarity is moles per liter, right? Don't I have 2 moles per liter down here? Right? That's what molarity is, moles per liter, moles per liter. And so to get my units, those fractions on the bottom actually flip out, and I get the units, which are the famous, we're going to call it the liter mole second, like the literhosen, the liter mole second, except in this case it's a liter mole minute, right, because minutes are on the bottom. So this is always your format, your template. Liters per mole, and your time values here. Usually this is seconds up here, but in this case it's minutes. Now, how many moles per liter are down here? 2? So this is going to be liters squared, moles squared per minute. So I would have to label this liters squared over moles squared per minute. I could also write that like this. I could write liters squared, mole minus 2, minute minus 1. All these do tell you is that they're in the denominator. Okay, they're in the denominator. Now, the easiest way to do this is the following. I'm going to go ahead and I'm going to solve for k. I've got my k value. Why is it erasing? It's turning on its side. So I have my value for k. Right, that's k. And now I'm going to go ahead and just very simply, this is k, look at my overall order. What's my overall order? 1 plus 2 equals 3. I know I have a molarity over here, just 1 molarity, right? 1 molarity is always rate. Molarity per minute, molarity per second. So I'm going to take my overall order, or I can talk tonight, and subtract 1, which gives me 2. And if you notice here, this matches my squared. So I solve for my value, and then I take my liter mole minute, or liter mole second, whatever the time unit is, and this becomes the exponent. Okay? So let's do one equation here. What if I had this situation? And if you understand this, just go ahead and buzz through this. So if I had molarity over here per second, that's rate, right, equals k, times this to the power of 1 and this to the power of 3. Finding k, I find the number. What are my units? The liter mole second in this case, right? That's my format. What's my overall order? 1 plus 3 equals 4. I've got 1 molarity here, so I'm going to subtract it. 4 minus 1 is 3, and so this becomes liters cubed, moles cubed per second. Right? What if this is only to the first order, and my units here were molarity per second, because it's rate, and I'm measuring per second. And this is A to the first power, whatever that is. Molarity is here and molarity is here. In other words, I have an overall order of 1, and I have 1 here, so 1 minus 1 is 0, isn't it? So what are my units? My basic template is liter mole second. This is to the 0 and this is to the 0, so isn't that just saying 1? So in this case, my units for equilibrium constant, excuse me, oh, I just said equilibrium constant. Can you believe that? That shows you how tired I am. For the rate constant, yikes, that's 1 over second. Okay? 1 over second. Now, the confusing part is that, just so you don't get confused, is that remember, rate is equal to rate law. So how do we find rate again? Concentration over time. How How do we find rate law? That, oh no, it also says rate, doesn't it? It says rate. This is how you find rate. Rate constant, baby K, not capital K. Concentration of whatever you have to a power. Why would you get confused again? Because they both say the word rate, but this is really rate, and this is really rate law. The two diagrams are completely different, right? Time and concentration for rate. Experiment 1, Experiment 2, Experiment 3 for rate law. We call this rate law the differential rate law. And the integrated rate law we're going to look at later. Okay? That's it for this podcast right now. Actually, I lie. We're going to go ahead and do mechanisms. Okay? So hopefully this is turning out with my microphone. So what's a mechanism? A mechanism is a process. So in your grandfather clock, you have a process. Any steps you have a process. There's a process to me doing this podcast. I make the background slides, I record it, I format it, I upload it to YouTube. Okay, and probably the slowest step is making the slides. So that holds me up. That's my slow step. Now, when you have a mechanism, this is what a mechanism looks like. Okay, you can't really see that, but these mechanisms are here. Okay, and I apologize. These two mechanisms, that doesn't make it better, does it? These are mechanisms that can fulfill two requirements to match a overall reaction and to match a rate law. So, two requirements for a mechanism to be plausible to match an overall balanced equation is that the elementary steps need to match the rate law. We'll talk about elementary steps in a minute. And the elementary steps must add up to equal the overall reaction. So the elementary steps need to match the rate law, and this is found by looking at the slow step. So the slow step has to match the rate law, and the elementary steps or the baby steps need to add up to the overall reaction. So I'm going to do one right here since you can't really see that one on the next page that well. So I have A plus B makes C plus D. This is my overall reaction. I'm going to give that to you. I'm going to tell you that that is true. Okay? Now, if I tell you that is true, will this do something here? Maybe not. Okay, because I must have typed that in there. It's supposed to move, but it doesn't. All right, so it's been a long week, hasn't it? So A plus B makes C plus D. That's my overall equation. We know this to be true, but we had enough advances in science that we've been able to slow things down. So all of a sudden when they slowed a reaction down, they started seeing in a closed container E appearing. Well, I don't see any E when you have A plus B equals C plus D, do you? And so they figured out that for this reaction, that there's actually a step where A bumps into A and makes E plus C. So you look at this, you think that A bumps into B and they simply make C and D, but that's not true. You need an A to bump into an A, and that makes E plus C. Well, what the heck is E? Well, guess what? You never see E because in the second step, so this is elementary step or baby step, elementary step. I'm not going to write this, I'm just going to go ahead and show you this right here. This is the elementary step right here, an elementary step, a baby step 1. Baby step 2, you take E plus B and you make another A plus D. And I'm going to tell you that this is a slow step, and I'm going to tell you that this is a fast step. They let you know that. So it's true here. If you just looked at the overall reaction, you would think simply that A bumps into B, making C and D. But when they slowed it down, they found that actually A bumps into A, making E, which is called an intermediate. This is an intermediate. What is an intermediate? An intermediate is made by one step and used up by the other. So it's made in this first step and is used up by this step. You never see it in the end, do you, if it's going really fast? If you slow it down, you see it appear. And so what's happening in reality here is that A is bumping into A, making E plus C, which is a product. But B can't do a thing, can it? What's B sitting around doing? B is sitting around waiting for E to appear. And until E appears, B can't do a thing. So sometimes they thought that reactions just took a long time to happen. They didn't know why. Now they know why. They can slow it down. Why do we call E intermediate again? It's made by one step and it's used up by the next, and you never see it in the overall reaction. That's the definition for an intermediate. Now, what's the first step? First requirement? The first requirement, or one requirement, is that elementary steps must add up to equal the overall reaction. These are the baby steps. Step 1 and step 2, elementary steps, slow and fast. Do they add up to equal the overall reaction? Well, here's a B, and here's a B. Here's a C, and here's a C. Here's a D, and here's a D. Here's an A, and here's an A. And you say, but wait, there's an A here and an A here. But guess what? You're starting with this A and ending with this A. You aren't adding it. It just means you have a bunch of A that bumps into each other, forming more A, which gets recycled back into this, and happens over and over and over again. So in reality, that A doesn't count, does it? So what do you get rid of here? E, because it's an intermediate. This A, because this A is just making more A to cycle back in, and there's your overall balanced equation. So look at that. Okay, now, if I were to tell you a rate law for this, I would say that the rate law would be rate equals K times A to the power of 1. So how do you do this? You look at the slow step to find the rate law. So if I say this is the rate law, I find the slow step. Where's the slow step? This step right here, right? Erase everything else so you can look at it. What are my ingredients in my slow step? Just that one A, right? That A right there. Okay, but what was written here? There was another A written here too, wasn't there? So if I told you this was the rate law, rate equals K times A to the first power, you would say, that's not true. That's not what the rate law says. The rate law says it's Ka to the second power, because these are the two ingredients in my slow step, and that matches the rate law. Let's try another one. Let's try the one on this page you can't really see real well. Okay, and I'm going to go ahead, I'll write it over. This is A squared plus, or not B, A squared, A to the subscript 2, diatomic B, diatomic R, plus C, and this is slow. And this is A2 here, plus R, plus C, and this is fast. I'm going to go ahead and add X, okay, so we can learn about something new. So from this, I want you to give me the overall balanced equation, and I want you to give me what you think the rate law would be. So what's the overall balanced equation? Well, I'm going to go ahead and tell you that I have 2C, diatomic B, and 2 diatomic A. That's my overall balanced equation. So let's look and see where I got that. I've got these right here. See how that matches? Now what's the deal with R and X? What was R again? What was something that was made by one step and used up by the other? If it's made by one step and used up by the other, right, the elementary step 1, the slow elementary step, and the fast elementary step, made by one, used up by the other is the intermediate, and you never see it in the overall balanced equation because it's used up. Now, what the heck is X? X right here is called a catalyst. What is a catalyst? Well, if you have a graph like this, it still happens. These are my reactants and these are my products. So in this case, this would be A, 2 of them, and B. And this would be 2C. What happens if I put a catalyst in here? You know, it makes it go faster. It provides a different pathway. Does it change where you start and where you end up? No, it doesn't. It just makes it happen faster. Okay? And I gave you an example in class. And that's why I don't include it, by the way, because I take this and use it over and over again. This right here, so I don't count it, do I? Okay, so there's my overall balanced equation. See that? If I have kids and they're going from point A to point B, right? Kids in this classroom and kids in this classroom. Okay? And I offer them candy. I say, if you get from A to B faster, I'll give you candy. They zoom. They'll go so fast. But if I don't give them candy, they still go to class. They still go from A to B. this graph right here. This is the graph that's with no candy because it's slower. It's harder to happen. If I give them candy, it makes it go faster. Did I change them going from A to B? I did not. So, again, where do you find this in a reaction? Where do you find the catalysts? You find a catalyst at the beginning and the end of an equation. I consciously put this in. I consciously have it left over. I take it and I save it and I use it again and again and again. But you don't see in the overall balanced equation. Why don't I see this in the overall balanced equation? Whatever this was, this is R. Because this is an intermediate. It's made by one step and used up by the other. Now, what would my rate law be? My rate law is this format. Remember, not concentration over time, but baby K. And I'd have whatever to a power. Now I got to look at what step? Not my fast step. I need to look at my slow step. So I'm going to erase everything else because this is too confusing to look at all this stuff. And my slow step, without everything crossed out on it, said this. I'm going to recopy it so you can see it. X plus A diatomic, B diatomic, makes R plus C. That was my slow step. That's what it said. So you tell me right now, what are my ingredients in my slow step? You might say that they are B diatomic, A diatomic, and X. But we already determined that X is what? A catalyst, so we don't count that. We don't look at these because those are my products. We look at these two ingredients in my slow step because that determines my rate. Right? My slowest process determines my rate. So I'm going to write A to the first, a little subscript of 2, B diatomic to the first, because I have one A and one B. What would happen if this is what my slow step looked like? What if I had, and it doesn't say that, but what if I had 2A? I would put a 2 here. What if I had 3B here? I put a 3B here. Make sense? What if I had no B here? Then it would just be this. Okay, so what are the two things that have meet the requirements to make a mechanism plausible? The elementary steps add up to equal the overall balanced equation, and I typically give that to you. And the slow step, you look at the reactants, and those reactants go right here in the rate law. Okay, and whatever the coefficients are in front of them, you put as exponents up top.